So why do we care about something else than the pressure-driven simulation, which just takes account for the pressure drop and through the momentum balance equations? Where, of course, one of the reasons is that these momentum balance equations requires careful tuning of these types of parameters, and in this case, Kozenik-Harman, this is like almost like a Bev constant, like linear driving force type of constant. And you see these parameters that we need to know in order to use these the organ equation adapted for our CSTRs in series model, right? So how can we do something that's as good as these momentum balance equations and maybe easier, but then we don't need to know these parameters. Well, that's where the no axial pressure drop comes in, right? So as you alternate to the pressure drop, this is called flow-driven approach. So in this case, what we're doing is actually the following. Even though it looks complicated, it's at the end of the day, we're just imposing certain constraint in our system. So one of the first constraint that we're interested in is this one. Pressure in the n CSTR is equal to the pressure in the n plus 1 CSTR. So if you think about this in a series of CSTRs, what we're saying is that in all these volumes of CSTRs, the pressure in those volumes are equal to each other across each and every time point for all time points, right? That's what's happening here, right? Yep, so basically since pressures are equal to each other but they're allowed to change with respect to time, based on these set of equations, which can be written for the first CSTR up to the NC minus 1 CSTR, NC being the number of CSTRs, right? We can actually derive equations based on that, because when we think about pressure, and since this is ideal gas situations, you can actually rewrite these as the product of concentration, total concentrations times temperature in each CSTR, right? That they're equivalent to each other. So with that, you can actually think about, index reduction here, right? So if you want to impose this constraint, what you need to do is you can actually take derivative of these constraints and then plug in the mass and energy balances, right? And then you're actually getting this equation 31, which is the basis of deriving all these different flow-driven equations. And obviously, it's complicated. However, once you do the derivation, at the end of the day, what you're getting is this system of linear equations, right? So basically, you're solving this system of linear equations in each time point during your simulation. And as long as you're able to solve this system, then you get the answer, right, for the pseudo-volumetric flow rates, the positive pseudo-volumetric flow rates and negative pseudo-volumetric flow rates. And it turned out that this A plus and A minus matrix is a special pattern, which they're tridiagonal matrices. And then when we actually consider the right-hand side terms, they also share some sort of patterns as well. So with that, the general formulation of this would be solving a linear program. By solving this linear program, we're able to determine the all the pseudo-volumetric flow rate in our CSTR model, CSTRs in series model. However, as you can imagine, solving these types of linear program in each time point during numerical integration is computationally intense. So we need an alternate approach. So all these alternate approach are discussed in this paper. Especially we developed guess and check algorithm so that we're only solving this linear program when that's necessary. So at the end of the day, without going into too much details, the takeaway message here is that there's pressure-driven simulation where it utilizes the empirical equation like momentum balance equation, organ equation, Kozenik-Harman. So that's the pressure-driven approach. And in addition to that, we developed the flow-controlled approach where we assume that there's no axial pressure drop, and then we can solve for these unknown volumetric flow rates based on the equations driven from those assumptions.